So, welcome to our brief crash course on X-ray, CAT scans, and gamma cameras. So first we'll talk about X-ray production. Typically you're going to have X-ray production occurring in an X-ray tube. There's going to be a filament on one side and a rotating plate on the other. Inside of that plate, you're going to have tungsten. It's a certain material that we're going to have the electrons crash into. These are just wires over here, and all of this is encapsulated inside a glass enclosure so that it becomes a vacuum, because we need a vacuum, otherwise you'll have interference from different air molecules whenever you're producing the electrons. So on the left side, you see it's negatively charged, right side's positively charged. The negatively charged is referred to as the cathode, and the positive charge is the anode. And there's a potential difference of energy, electrical difference of energy rather, between the two. The cathode's much lower, anode's much more positively charged. And as electricity begins to flow through the cathode, the kinetic energy of the electrons in that material, whatever it may be, begins to build, and those electrons are freed from that process and they shoot over to the tungsten anode because it is so positively charged. It attracts them over there and they collide with that. When they do, most of the energy is released as heat. So 99% of that energy is released as heat, and only 1% is used in X-ray production. So you can see that the tungsten is angled to try to deflect the X-rays downward in that direction, and they'll go all over the place, but if we can angle them down, that's what we're really going for. And when they do go all over the place, there's typically lead shielding around the apparatus to prevent those X-rays from encountering another person that it's not intended to, or go to another area that it's not intended to. So because it heats up so much, there's a rotor connected to the back of that tungsten anode that is really rapidly rotating it to help dissipate that heat. And so there's two main mechanisms that we get X-ray production from. One of which is going to be the Bremsstrahlung mechanism. We're just going to abbreviate that as Brems, and the other is characteristic. Now, if we look at a little graph here of on the y-axis, we have the intensity of the X-rays produced and the energy of the X-rays produced. So we could see here it's kind of this smooth swooping motion, and then we have these little peaks in between there. And the smooth production underneath is the Bremsstrahlung production, and those peaks of X-ray production are characteristic. And we'll explain why those are that way in just a second. So we'll look at Brems here, and hopefully our illustrator will realize momentarily that his camera is a little too low, and that'll be adjusted. But we'll see here the electron is traveling near the nucleus of our tungsten that we have there on our anode, and it bends around that nucleus of the tungsten atom. And it doesn't directly interact with it, but it just bends around it. So before it bends, it has an initial kinetic energy, and then after it bends, it has a final kinetic energy. And as it bends around that, it's slowing down when it turns. So it's losing that kinetic energy. So we know the initial kinetic energy is better, or greater rather, than the final kinetic energy. And that difference in kinetic energy is proportional to the energy of the X-ray that's produced. So that's one way we get it, and that range is based on how close it is to that tungsten atom. So that's why you kind of get a range, a consistent range of those X-rays produced, and you can kind of see there's much more specific range for those characteristic X-rays that are produced, and that is based in how they're produced. So we again have our little atom that has multiple electron orbitals going around it. And we can see there's different orbital shells, so that inner one is K, and then L, and an M moving on outward. but we like to call that inside one commonly K, because that's kind of like our ground state. So we can see an electron coming in, and it collides with an electron in that K shell. So that smashes the electron out that was encountering it, and the K shell electron. So both of those electrons leave. And we'll see that electrons from the outer shells, the L and the M shells, will move down into the lower shell. And when they do that, they lose energy. They're going to a lower energy shell, so they have to adapt to that. And they give off that energy as an X-ray photon as they move down. So because that X-ray photon released is a specific energy change between those levels, that's why you get those peaks in the characteristic X-ray graph there, because it's specifically those energy ranges that are occurring from degrading through electron shells. So there's also different attenuation mechanisms. And what is attenuation? Well, this is what's happening inside the body after those X-rays are produced. They travel to the body. And basically any kind of attenuation is a decrease in energy as the X-ray or the particle moves through an absorbing material. And you can also think of the energy as intensity as well. So how does attenuation occur? Well, let's look at the formula for attenuation first. So we have I equals IOE over to the power of negative mu x. So I would be the transmitted intensity that we get after it's moved through an absorbing material. IO would be the initial intensity of that photon before it is attenuated at all. Mu would be the absorption coefficient, which is proportional to z cubed, z being the atomic number of the atom that it's interacting with. So the absorption coefficient is a property of the absorption material. So the more higher atomic number that material has, then the more absorption will occur. So for instance, and x is the thickness of the material, the distance traveled through the material. So for instance, bone has a greater mu value than soft tissue mu does. And again, our illustrator will move that graph up, and we'll see that as that X-ray photon travels a distance and then enters the body, it will lose energy much faster as it travels through bone than it will soft tissue, because the attenuation coefficient is so much higher. So a couple things occur when absorption occurs, one of which is the photoelectric effect, and that typically is dominated by X-rays that are lower than 100 kiloelectrovolts, and that's because once it gets to a higher energy level, it will continue on. So with the photoelectric effect, we have an X-ray proton that collides with an electron of an atom and shoots that electron out, and the X-ray photon is totally destroyed. There's no more energy left, and this just leaves a ionized atom. And then the other method is the Compton scattering. We see an X-ray photon again collide with an electron, and then the X-ray photon is not totally destroyed and continues onward, but the energy is decreased. So the initial energy of the X-ray photon before is greater than after it scatters. So that's the basics of attenuation. So we'll move on to how this creates an image. So now we can move on to how a image is created using these mechanisms that we just saw. We know how the X-rays are produced. We know how they travel through the body. Now we're going to look at how they're actually producing an image on the other side with the screen. So we have two different sources of detection of those X-rays, and one is a film source and the other is a digital source. So the film is just kind of detecting based on a chemical reaction that occurs. It has pretty good spatial resolution at about 0.08 millimeters, and there's also a digital option that it has a little worse, but still pretty good spatial resolution at 0.17 millimeters. And the resolution of the film is limited by the focal spot and detector resolution, whereas the resolution of the digital radiography is only limited by the detector elements and just kind of like the pixels that are able to pick up the X-ray. So if we look at the digital, you could see that the X-rays encounter individual pixels on their own, and based on the energy level of those X-rays will determine how dark that computer generates that image. So it'll give it a number, it'll assign it a number, and you can see that 3 different X-rays are numbered 112, and as the computer analyzes it, says, okay, this is this energy level, it's going to be this color, this one's this energy level, it's going to be this level of darkness, and this is this energy level, so it'll be much darker than the other two. And that's just a basic rundown of how those digital screens process images. Now there's 2 components to creating a good image, creating a clear picture. You're going to have contrast, and you're also going to have spatial resolution. Contrast, you can define in a formula with 1 minus e to the negative mu2 minus mu1 times x. And those mu's are just the difference between the 2 materials that you're imaging between or contrasting between. Another key element to how well the image comes out is the geometry of the system. And when we say geometry of the system, it's pretty much where the X-rays are coming from in relation to the body, in relation to the screen that they're being detected from. So in this diagram, you could see that all X-rays are diverging rays. So based on that geometry, we want them to diverge as little as possible to prevent blurring. And you can see those little black spots, those represent geometric unsharpness, but we will just call it blur. And so that source size has a pretty big impact on that blur. So if we shrink down our source size, we decrease the point of which the X-rays are diverging, we can decrease that blur. And by doing so, we can increase the sharpness and spatial resolution of our image. You can see the black dot has gotten much smaller, so our source size decreased, which decreased our blur. So the geometry of the system here, we could see the distance between the system between the X-ray source and the body would be A. Distance between the body and the screen would be B. So if we're going to increase spatial resolution, we're going to want to increase A and decrease B as much as we can. And that way we can increase the spatial resolution of our image. Now there's times where the contrast is not exactly where we want it to be, and we'd like to increase that contrast. So the radiologist may use a contrast medium that the patient drinks to increase the contrast between these 2 mu values. Typically we'll use something like barium because it has a very large Z value, and that large Z value increases the contrast between the 2 mediums.
CT stands for computed tomography, and it's much like X-ray in that X-rays are still produced from an X-ray tube, and there's still a detector with the same digital detection on the other side of the X-ray tube. Now, there's also some key differences. Because of the nature of the CT, there's a restricted system geometry. The CT also utilizes back projection, and it creates a 3D image, and this also creates a better contrast between soft tissue. So as I said previously, this X-ray tubes, there are still X-ray tubes in the CT scan, and there's still a detector, and the X-ray tubes still diverge from the X-rays still diverge from the source, and the difference in attenuation coefficients and how it's absorbed in the body is what yields this image. Now, when the CT starts to revolve around the patient is slowly sent in, and the CT takes hundreds and hundreds of cross-sectional images, which it then compiles to create the 3D image that results. And again, the main difference in X-ray and CT is that CT takes cross-sectional images, which it then compiles and stacks upon one another to create the 3D image. And it does this by utilizing back projection, which is essentially the CT creating an image from the light that it does not detect. And the spatial resolution of this machine is around 0.4 millimeters. So this is a brief and small diagram of back projection where the X-ray sources are from the top and from the right, and the detectors are obviously on the other side. And you can see that there is an area in the diagram where the detector does not receive some light. And again, this is how the CT takes data and images and things of that nature.
Gamma camera, form of nuclear medicine. First of all, radioactive isotopes are created when a proton is introduced to a cyclotron, or a particle accelerator. The proton is accelerated towards a stable atom where they collide, creating an unstable nucleus, producing a radionuclide. Usually it's technetium-99. This undergoes spontaneous decay, producing stable daughter nucleus, along with beta, alpha, and neutron particles that are absorbed by the body. And the radionuclide produced emits gamma rays. So we have a physical half-life, which is the time required for half of the substance, in this case technetium-99, to undergo radioactive decay. We also have a biological half-life, which is the time required for 50% of the substance in the form of gamma rays to be emitted to or from the body through metabolic turnover. The effective half-life is both of these combined, as shown in the equation. So the whole process together is technetium-99 is injected into a patient, and through the metabolic turnover, gamma rays are emitted from the body. Into a collimator, which is usually lead. The lead collimator blocks most of the diverging gamma rays, and only the rays that are emitted straight through go into a scintillation crystal. The scintillation crystal then produces photons, which are then introduced into the photomultiplier tubes to the CPU to create a digital image. Now the collimator plays an important role in getting the most out of the spatial resolution. So we have A, which is the distance between the collimator and the patient. This is important to have the least distance possible in order to increase spatial resolution or mixing of gamma emissions. We also have the septum size of the collimator itself, which needs to increase the spatial resolution and decrease mixing. The length of the collimator needs to decrease in order to increase spatial resolution. And the diameter of the collimator holes need to decrease to increase spatial resolution. Overall, spatial resolution of a gamma camera is 7 millimeters, which is much less than X-ray and CT. Gamma camera is beneficial due to the functionality and contrast, along with the greater intensity of back projection. Disadvantage would be the high energy due to the increased sensitivity of the detector, which causes low spatial resolution. And the collimator also affects the decrease of spatial resolution along with the scintillation crystal.
Thank you for following along with us. All references of information were provided by our class notes in the Physics of Medical Imaging course at Rockhurst University and from the Introduction to Physics and Modern Medicine by Suzanne Amador Kane.